In this section, we're going to talk about how to find the area between two curves. And so if we want to find the area between two curves, from again a to b, those are our limits, we're going to use the formula where we take f of x and minus g of x. Then we're going to integrate that from a to b. Now, when you set this up, f of x needs to be the higher function. Or in other words, when you subtract, make sure you put the higher function first. As long as you do that, you're going to be okay. So in this example, let's find the area between y equals 6x. Oh, this is y equals negative 6x, and y equals 3x squared. You'll see it's always nicer to go ahead and graph these before you get started with your problem so you can kind of see what's happening. So if we want to find this area between them, notice we're going from 1 to 5, so here's my 1, here's my 5, we want this area in between. So we're going to integrate from 1 to 5, and we're going to integrate. Okay, now make sure you take the top function. Which function is higher? In this case, the parabola of y equals 3x squared is higher. So 3x squared minus the lower function. So minus, our lower function is negative 6x dx. And that will just cancel to a plus. And now we integrate. So this is going to be 3x squared over 3 plus 3x cubed. And 6x squared over 2. And we're going to evaluate from x equals 1 to 5. So this will be, let's simplify this first. This is x cubed plus 3x squared, evaluated from 1 to 5. Okay, so now we have 5 cubed plus 3 times 5 squared minus, and then we'll do 1 cubed plus 3 times 1 squared. So this should be 171 if I put it all in correctly. So the area in between those two curves from 1 to 5 is 171. Actually, no, sorry, if I double check my work, I put in a 2 and I meant to put a 3. So this should really be 196. That is one problem. You're doing so many computations, you have to check very carefully to make sure you don't mess up. Okay, so that's a very simple problem where we just said, okay, we subtract the two functions. We went from 1 to 5. We're good. Now though, let's change this a little bit. Okay, notice when you had the parabola and the line that they actually cross in a few places. So now what if we want to find the area from negative 2 to 5? So here's my negative 2, here's my 5. We want to find the area in between the curves. Well, notice over here, the line is actually on top, and over here, the parabola is on top. So these curves cross, and we always have to have the higher curve on top when we integrate. So that means we're going to have to break it up into two pieces. So we're going to have to integrate from negative 2 to 0, and this time we'll put the line on top because the line is higher. So the line is higher here, but here the parabola is higher. So when my line is higher, I put that first, so negative 6x minus 3x squared from negative 2 to 0. Plus, now I'll do my second section. So my second section will go from 0 to 5, and there my parabola is higher, so we'll do 3x squared minus my negative 6x. Oh, dx. dx, you need to always put the dx. Now at this point, we've done a lot of integrals, definite integrals in the last two sections. I'm not going to keep doing the actual work here because I'm showing you how to set up the curves. When you're doing this on your own, you will need to finish working all of this out. But for now, I'm going to just go ahead and skip to the answer. If you still need help with how to actually work it out from here, you can go back and look at the last two videos again. So doing all the work, getting it all done would be 205. So again, we're just going to work on how to set this up. If you still need help with how to evaluate it, go back and look at the videos for section 6.2 and 6.3. So in this case, let's find the area bounded by the two curves of y equals 3x, here's y equals 3x, and negative 5x squared. And notice it didn't give me limits. It just said find the area bounded by the two curves. So you'll notice right here, this area, it doesn't actually have to give me limits, because when it crosses at this intersection here and here, that's going to completely bound the area. So what we need to do is we have to first find the intersection. Okay. So how do you find the intersection of y equals 3x and y equals negative 5x squared? What you do is you say, well, this is a y equals, this is a y equals, let's set them equal to each other. So we do 3x equals negative 5x squared. At this point, I would bring them both to one side, 5x squared minus plus 3x equals 0, and I would factor. So x is going to be x times 5x plus 3 equals 0, and I'd say x equals 0 and x equals negative 3/5. So this point is x equals negative 3/5. This point is x equals 0. So those are my limits of integration. So I had to actually find those first. So now we can integrate from negative 3/5 to 0. Which one is on top? In this area that I'm looking at specifically, the parabola is on top, so we'll do negative 5x squared minus 3x dx. Okay, again, set this all up, put it in your calculator. No, sorry, don't put it in your calculator. You need to do it by hand because you're still learning how to do it by hand. And you're going to get 0.18. Now again, we mentioned how it's good to graph these out. So when I kind of graphed it, I had an idea of, okay, they intersect each other, they're bounding it, I need to look for my limits of integration, I could kind of eyeball about what they might be. So if you don't have a graphing calculator, you can go use wolframalpha.com, and let me show you how this works. So Wolfram Alpha is a free site that can calculate a lot of things. It can actually do almost everything we do in this class, and you are welcome to always use it to check your work. Just make sure you don't use it instead of doing the work, because of course you don't have it on the exam. So in this case, I would ask it something like, okay, in this problem I want to know the area between these two curves. So I would say area between 3x and negative 5x squared. It thinks for a minute. It tells you area between 3x and negative 5x squared. Notice it set up the integral from negative 3/5 to 0. It told us my answer, and it did a nice little graph for us. So again, if you don't have a graphing calculator, you can do this. You could also say something like, might want to integrate or integral. Let's say I want to find the integral of x squared from x equals 2 to x equals 5. You could type that in, and it will show you that you have the integral from 2 to 5 of x squared is 39. It will even show you a nice little picture and show you it's finding the area under x squared from 2 to 5. So that's just a nice little website you can use. Back to this, because there's a lot of different theory that we're going to pull into how to find the area for different situations. So that's again why we're just kind of going through. I'm showing you how to set up all these problems, and then you can go through and figure out how to actually evaluate them and do the actual integral later. So let's find the area under the curve y equals x minus 3 from x equals 4 to x equals 6. Notice this is just the area under the curve. It didn't say two curves or anything. And this goes back to what we said in our last section, section 6.2, where area under a curve is defined as the area between the curve and the x-axis. So when you look at this picture, it's the area under that curve, but where does it stop? It stops at the line y equals 0. So this is really between y equals x minus 3 and y equals 0. So when we integrate, we would integrate from 4 to 6, and we would do x minus 3 minus 0 dx, where this is one function, this is the other function. Now notice what's going to happen when you subtract 0. Every single time, it's not going to make a difference, right? And so I'd just be back to the integral from 4 to 6 of x minus 3 dx. This is why, if you want to find the area under the curve, they just define that as above the y-axis, or above the x-axis, and we didn't have to do anything special. It turns out that they truly are subtracting 0 every time, you just don't bother doing it because it doesn't make a difference. But now I might change my example slightly, and I might still have that same curve, but what if I wanted to find the area over here, where my curve was actually under the x-axis? Now an area, by default, should be positive, right? Okay. We don't want to get a negative area, but if I just integrated from 1 to 3 of x minus 3 dx, I would get a negative answer. I would get negative 2, and that doesn't make sense. We can't have negative areas. So let's see what we did wrong here. We just integrated x minus 3, but if you look at this, what is actually on top? It's like you have two functions. You have the function y equals 0 and y equals x minus 3. So when I integrate this, I go from 1 to 3, but I say which one's on top? In this case, the function 0 is actually on top, so it's going to be 0 minus x minus 3 dx. And when I integrate that, I will get positive 2, which is much better. And so again, it's that y equals 0, that was really on top, so I need to do 0 minus my function that's on bottom. Now our textbook has actual formulas for this. So they'll tell you if your function or your curve is above the x-axis, then to find your area, is going to be the integral from a to b f of x dx. But if your curve is below the x-axis, then our area is going to be equal from a to b, but you have to do 0 minus your function. So it's always going to be negative f of x dx. So if your curve is below the x-axis, you have to put the negative there. Or you can just remember, oh, I have to do my top function of 0 minus my bottom function, which is what I'm actually interested in. That's where that negative comes from. Now, what if we have a situation like this, where my curve crosses the x-axis, or my line crosses the x-axis? So in some places my line is below the x-axis, sometimes it's above. So we have to split it up. We're going to split it right here at 3 where it crosses. So we'll do the integral from 1 to 3. And in this case, we'll do the one on top is the x-axis of 0. So we'll do 0 minus x minus 3 dx. Plus, okay, and now I go from 3 to 6. And in this case, which one's on top? Now my line is on top, so I'll do the x minus 3 first, and then I'll minus 0. Okay, try this yourself, and the answer is 6.5. Okay. Oh, and here's the remark. I actually put it in officially. So if your curve, f of x, is below the x-axis, then when you integrate, you'll get a negative result. So that's what happened up here when we just integrated our function. We got a negative result. So instead, if you're thinking about area, if your curve is below the x-axis, you would integrate negative f of x so you can get a positive area. Now there's a few applications in this section. So the first one, let's say we have a rocket fired vertically into the air, and it does start 10 feet above the ground. We know that our velocity is negative 32t plus 160 feet per second. And there's a few things we might want to find. So we might want to find the displacement, which is just how much does the position of the rocket change from 0 to 8 seconds. So I've graphed here for you the velocity, and I've also graphed the position function. So velocity is the derivative of position. So notice my rocket, it started off at the bottom, and then as time went on, it went higher and higher, but then at one point it turned and started falling back towards the ground. So where did it turn? Well, it should turn wherever my derivative is 0, or right here at 5 seconds. So it started turning at 5 seconds. And that's just kind of an interesting note, which we'll use later. Okay, but how much did my position change? So I went from 10 to 266. So it should change by 256. Now let's actually integrate this to see how we can do it. So anytime we want to know how much you changed, we're looking for what's called in our textbook the net change. And if you want to find the net change and you know the derivative, you integrate the derivative and that will give you your net change. So in our case, we could just integrate from 0 to 8, our negative 32t plus 160, and get 256. Okay, which matches what we had on our graph. So I changed from 10 to 266, so that's a difference of 256. But that's just kind of how much I changed between those two times. Notice how my rocket went up, and then my rocket started going back down. So from here to here, it traveled almost like 400 feet, and then it went back down, so it traveled kind of up 400 and then back down over 100. So all told, about 400 plus 150, it traveled maybe 550 feet total from 0 to 8 seconds. So how would we actually find that mathematically? Well, what we would do is we say, okay, my rocket had positive velocity until 5 seconds, and then it switched to negative velocity. So my velocity is positive until 5 seconds, then it's negative. Or if you look at your position, I was going up till 5 seconds and then down. So if I want to see how much my total distance changed, I say, well, let's integrate from 0 to 5 my velocity of negative 32t plus 160. And then let's integrate from 5 to 8 of my negative 32t plus 160. And if I do those two integrals separately, I should have this piece and then this piece, and then I can see how much the total is. But now notice, if you calculate this piece, you're going to get a positive. If I calculate this, notice that my velocity was underneath, and if I'm integrating right here, that's going to be a negative area. So how will I fix that? I'll put the negative out in front so that I get a positive answer. So you'll see down here where I showed you, and when we integrate from 0 to 5, we got 400. If I integrated just my normal function from 5 to 8, I got negative 144. So that's kind of telling me we went up 400 when it's positive, and then I went down 144, that's why it was negative. So if I put a negative out here, I can switch that to 144, and so our total distance traveled is 544. And now let's talk about our business. So anytime you know the derivative or rate of change of profit, now you could put in here cost or revenue or almost anything else you can think of. If you know the rate of change of anything, then you can take the integral to find the total profit between A and B. So in this case, if our profit is changing at a rate of, notice this MP, that stands for marginal profit, or that's the derivative of profit, of 1 over x plus 3.4x squared per unit, find out how much the profit increases from x equals 10 to x equals 25. Well, if that's our marginal profit and we want to know what the profit is, we integrate it, and we're interested from 10 to 25, so those are my limits of integration. Now what if we had another situation where we have two marginal profit curves? Okay. Or in this case, we believe that, continuing our example, if we switch to a new production facility, we'll have a new marginal profit, okay, which is 1 over x plus 9.3x squared. And we want to know how much more profit would we make if we increase from 10 to 25 if we use the new production facility. Or we kind of know what's the area between those two curves from 10 to 25. And so again, I would graph it just to see which one's going to be on top. It's going to be the 9.3x squared on top. So I need to integrate from 10 to 25. And I'm going to put the function on top. That's first, minus, and then put the function that was on the bottom. And integrate that. And that will tell us the total difference for our total profit if we switch, or what's the area kind of between these two curves. Let's go ahead and actually work this one out. So 10 to 25, notice your 1 over x's will cancel. So we just have 9.3 minus 3.4, or 5.9 x squared dx. Okay, so when I integrate this, I'm going to have the 5.9 the x squared we raised by 1 power, so to 3, and divide by my new power of 3. And we will integrate from x equals 10 to 25. So we'll have 5.9 times 25 cubed over 3 minus 5.9 times 10 cubed over 3. Or 28,762.5. That would be, again, the difference in the total profit if I switch to my new facility.